for the delay.
No problem. Okay, ready?
Yes.
So everybody, thank you for coming to a very unusual and special meeting of the Graduate Online Combinatorics Colloquium. Today we have one of the organizers, Alex McDonough, here to talk to us about chip firing on representable matroids. So just as a heads up, this talk is recorded, as you may have noticed. I'm going to be monitoring the chat, so you should be able to unmute yourself and ask a question, but if you don't have a microphone or you can't do that or you don't want to, I'll be monitoring the group chat and I will interrupt Alex with questions as needed. Okay, take it away.
Thanks, Galen, and thanks everyone for showing up. So today I'm going to be talking about chip firing on representable matroids. First, I want to talk about what chip firing is in the traditional sense. So we're going to have a graph, and we're going to put numbers on the vertices of the graph. And these all have to be integers. And we can think of these as chips. I don't know what kind of chips. I think usually people do poker chips. I usually think of potato chips because it doesn't make any less sense. But we have numbers on the vertices of our graph. And what we're going to do is we have this thing called firing a vertex. So let's say we want to fire this upper left vertex. What happens is we're going to take one chip and send it along each of the two edges. So in this case, the number on that vertex is going to go down by 2. The chips are going to move across, and then they're going to land at this spot, and these are each going to get one more chip. So this is what happens before the vertex is fired, and this is what happens once the vertex is done firing. We can see another one. If we were to fire this vertex, then it would shoot one chip in each of these places, and this would be the end result. This is also sometimes called like the dollar game, or there's other things. That's when people are sending money around, trying not to go into debt. A lot of times there's rules for when you're allowed to fire. Sometimes you aren't allowed to have negative numbers on the vertices, and sometimes you can't fire if you make something go negative. In the version that I'm going to be working with, any type of firing is allowed whenever you want, as long as you like do a full firing. You can't do fractional or anything like that. And you're also allowed to do an unfiring. So if I wanted to unfire this bottom right vertex, then I would sort of suck in one chip from the adjacent vertices, and then there'd be 2 more chips on that vertex. So first question we might ask, does the order of firings matter? And especially with this model where you're allowed to go in whatever, you're allowed to fire whenever you want to. It's probably easiest to see that it doesn't matter what order you fire vertices. And even in the other models, it's generally there's this idea where it doesn't matter what order you fire things. So it's called the abelian sandpile model because the order of firings doesn't matter. And then we're going to say that 2 chip configurations are firing equivalent if we can get from one to the other by firing moves. So all of the chip configurations you've seen so far have been firing equivalent. And it's not hard to show that it's an equivalence relation, since you can just unfire every firing. It's easy to go backwards or to do one set of firings and then another. That'll give you what's it called? A goes to B goes to C, whatever. So we have our equivalence relation, firing equivalence. And now we might ask, are there any chip configurations that we definitely can't get to? So does someone want to unmute themselves and tell me a chip configuration you can't get to?
1/2 pi square root of 2, 9.
1/2 square root of 2. So there's one. You can't get, but then that's not a chip configuration because they're not integers in the vertices.
Just have different sum.
Yeah, different sum, exactly. And there's other answers, but this is the easiest to see. We're never going to change the total number of chips on this graph. We're just rearranging them. So if we have a sum different, then that's going to that's not going to be a firing equivalent chip configuration. Okay, so we're going to just work with chip configurations that have 0 total chips, which in the last one you can see there's 0 total chips. We're going to call these chip configurations cyclic chip configurations. And I should warn you now, things are going to sound a lot like topology, and people who are topologically inclined might ask, oh wait, isn't that this? You'll see in a few slides that that is this, and then everything will come together. So anyway, we have our cyclic chip configurations, and we're going to define the Sandpile group as the group of cyclic chip configurations under pointwise addition. So we just add the number of chips at each thing, modulo firing. Did someone say something?
Thank you. Thank you.
Okay. So it's the group of cyclic chip configurations under pointwise addition modulo this firing equivalence relation. So if you can get from one chip configuration to another by a series of firings, then they're equivalent as elements of the Sandpile group. And there's a million names for the Sandpile group, or at least 4, depending on what perspective you're coming from. This shows up a lot in algebraic geometry. So you got the Picard group and the Jacobian, and the critical group is sort of from a separate perspective, but they're all the same thing, and it just shows up a lot in a lot of different contexts. And this is sort of the classic result, in my opinion, maybe the most important one about why the Sandpile group is interesting, which is that the size of the Sandpile group is equal to the number of spanning trees of the graph, which are like the maximal sets of edges that don't contain any cycles. So somehow this group that seems to have nothing to do with spanning trees is going to count the number of spanning trees of our graph. And I'm going to prove this in a really roundabout way that proves more things. So we'll get to this later. But if you set it up right, it comes from Kirchhoff's matrix tree theorem from back in the 1800s. So that's why it's called Sandpile matrix tree theorem. So instead of working with chips on the vertices, we're going to have some chip trucks that are driving from vertex to vertex. So this is basically putting chips on the edges. So let's say we have these trucks. We have 1 truck going from here to here. We have 4 trucks going from here to here, 5 from here to here, and 1 from here to here. And then what we can do is right now we have arrows on our chips, which is a little confusing. So we're going to choose an orientation of the graph, and that's going to be able to get rid of the arrows. So if we chose this orientation, we can put these numbers in the graph. So this would mean that there's 1 truck going from here to here, 1 truck going from here to here. Since this is a -5, this actually means there's 5 trucks going from here to here. So by giving an orientation on the graph, we're able to just put numbers on the edges instead of needing numbers and some sort of direction that we have no way to describe. And something that I want to point out that's very important and easy to miss is that this is not a directed graph. You can define chip firing on directed graphs, but we shouldn't think of it like this. This is an oriented graph, and the orientation doesn't change anything. It's just for bookkeeping. So if we had this edge on the right oriented in the other direction, for example, that just changes this -4 to a 4, and it's not going to change anything about how many trucks are moving from one vertex to another. So remember that this orientation is just for us to keep track of which direction the trucks are going. It's not actually a direction on the edges of our graph. So I'm going to call an assignment of an integer to each edge of an oriented graph an edge configuration. Is there a question? Oh. Potato, yeah, someone wants to fire chips in real life. So yeah, an edge configuration, we're going to put an integer on each edge instead of a chip configuration puts an integer on each vertex. So this is an example of an edge configuration. And we can get from a chip configuration or from an edge configuration to a chip configuration by having each truck take 1 chip from its starting vertex and delivering it to the ending vertex. So in this example, this truck is going to take 1 chip from here and deliver it over here, and then nothing's happening on this edge. So this vertex is going to get a 1 on it. And then like this vertex has 4 chips leaving and 1 chip coming in, so it's going to get a -3 on it. And if we do this, we can call this map del, the boundary map from edge configurations to chip configurations, and people who do topology are going, or even people who have just kind of seen some topology are probably going to recognize this boundary map. And I'll talk more about the connections on the next slide. Maybe 2 slides. So something that we can note is that this boundary map is always going to map to cyclic chip configurations, which remember means there's a total of 0 chips. So in this example, we see that there's a total of 0 chips. And the reason for this is because each truck is going to put a chip somewhere and then put a negative chip somewhere. So each truck is actually having no effect on the total number of chips. So now we're going to say what edge firing equivalent means. So 2 edge configurations are edge firing equivalent if their boundaries are firing equivalent with respect to the chip firing equivalence relation. And then we can define the edge labeled sandpile group. This isn't really a real thing that people use, but this is something that I thought was helpful to define. This is the group of edge configurations under pointwise addition modulo the edge firing equivalence relation. And we can see the similarities between this group and the traditional sandpile group. Instead of the normal firing equivalence relation, we have this edge firing equivalence relation. So these are closely related. And now it's topology time, where we can see just how closely related are they. And now we got even more exclamation points because it's very exciting. So chip configurations are also called 0 chains. And the group of 0 chains under pointwise addition is denoted C0. Similarly, edge configurations are called 1 chains, and the group of them is C1. And if we have epsilon be the map from C0 to the integers that outputs the total number of chips, then the kernel of epsilon is going to be exactly the group of cyclic chip configurations, because the group of configurations that have a total of 0 chips. We have this map, the boundary map del from C1 to C0. So we get this pair of maps that takes us from C1 to C0 to the integers. And we already observed that the image of this del is contained in the kernel of epsilon. The way we did that is by saying that the boundary map always maps to cyclic chip configurations. So we have a group, the kernel of epsilon divided by the image of del, and this is the 0th reduced homology group. So this is a super important object in homology theory, and it just pops up from playing around with chip firing and looking at chip firing on edges instead. So I thought that was pretty cool that you actually get this homology group just popping up. And it also made me understand what homology is coming from a little bit better. So now we can actually look at how the sandpile group and the edge labeled sandpile group are related. So the sandpile group is dealing with cyclic chip configuration, so it's the kernel of epsilon. The edge labeled sandpile group is, it's saying any 2 edge configurations with the same boundary are considered equivalent, so we're really working with the image of del, not all of C1 in this case. So, and these both have the same equivalence relation, which is firing equivalence on vertices. So that tells us that the sandpile group and the edge labeled sandpile group are going to be isomorphic if and only if this 0th reduced homology is trivial. And there's this classic result from homology theory that the 0th reduced homology group is going to be Z to K minus 1, where K is the number of connected components. So in other words, it's going to be trivial if there's 1 connected component. And if there's more connected components, then it's not trivial. In general, we can say that this edge labeled sandpile group of G is going to be the direct sum of the Sandpile group on each connected component of our graph. And the Sandpile group of our graph is going to be infinite because there's no way to transfer chips from one connected component to another. So if we have one connected component with one total chip and another connected component with -1 total chips, that can never go to anything that has 0 chips in each. So now we want to play around with this edge-labeled Sandpile group. So we already have this definition from before where 2 edge configurations are edge firing equivalent if their boundaries are firing equivalent as chip configurations. But this definition doesn't really seem to help us at all because all we're doing is taking these and turning them into chip configurations and looking at that. So we want to try to come up with a better definition that doesn't rely on turning stuff into chip configurations again. So let's take a close look at this del map. We can write it as a matrix where the columns correspond to edges and the rows correspond to vertices. And then we put a 1 or -1 when we get a vertex corresponding to an edge based on the direction of the orientation of that edge. So this is another way of writing this partial, the del boundary map. And now we ask, what happens when you fire a vertex? So let's say that we fire vertex B. We're going to subtract 2 from B. We're sort of subtracting 1 in this direction and 1 in this direction. Then we're going to add 1 to C and add 1 to A. But we could also think of this with respect to edge configurations as we add 1 chip truck going over here, and then we have a negative chip truck going this way because we want 1 chip truck going this way. So this turns into this. And the cool thing about this is that if we look at the row corresponding to B, then we get 1 for AB and we get -1 for BC. So firing B is exactly the same as subtracting the row that corresponds to B. And that also means that if we do a bunch of firings, that's going to correspond to adding some integer combination of the rows of our boundary matrix. So we're going to add some element of the image of del transpose. But there's a new type of firing that we get that we didn't have before, which is we can add a 1 chain whose boundary is trivial. So for example, if we add this 1 chain, it's sort of like having a truck that's going all the way around. This isn't going to change the boundary at all. So in particular, it's not going to change the edge firing equivalence class. So what do these correspond to? So if we look at the columns of this matrix corresponding to these edges, we see that if we take the combination of them given these signs, then we're going to get 0. So in this case, if we take AB plus BC plus CD minus AD, that's going to give us 0, 0, 0, 0. In other words, when we do this type of firing, this is going to add an element of the kernel of del. And it follows that we can come up with a better definition, or at least more helpful in our future case, of edge firing equivalence by saying that 2 edge configurations are edge firing equivalent if their difference is in the direct sum of the image of del transpose plus the kernel of del. And I didn't completely prove this, but hopefully it's believable that these are kind of the only 2 types of firings that we can do. Any questions? All right, so we have our cool new edge firing equivalence relation. Let's talk about matroids now. So a matroid is a pair E fancy B, where B is a subset of the power set of E, and it satisfies some conditions. They're pretty easy to state, but I don't want to detract from the main part of the talk, so I'm not going to give them right here. But I do encourage everyone to learn about matroids because they're great and wonderful and make me happy. E is called the ground set, and B is called the set of bases. And for this talk, we're only going to care about what's called representable matroids. So how do you get a representable matroid? You're going to start with a matrix, and I'll just skip to the matrix here. The columns of the matrix are going to form the ground set, and the maximal linearly independent collection of column vectors are the bases. So in this case, the ground set is made up of all of the columns, and then the bases are all of the sets of columns that are linearly independent. And this is a really nice definition because the bases are exactly the bases in the linear algebra sense. So like I like this definition. Everyone kind of has their own pet idea of what you think of when you think of a matroid, and this is one of my favorites because you actually have the basis having like you see exactly where the word bases comes from because it is a basis when you look at it in the linear algebra sense. Okay, so we have our matroid. We have so we have E and B for this particular case, and there's matroids that can't be written this way that don't come from matrices. Those would be called non-representable, but we're not really going to concern ourselves with those for now. So what happens if we take this boundary matrix of a graph, we take del in matrix form, and we turn that into a matroid? What do we get? Well, first of all, the columns are going to correspond to the edges. So we know that E is edges, which is actually why E is the letter that they choose, I'm pretty sure, because one of the original things people were working with is graphical matroids when matroids were defined. So E is edges, that's not too hard to remember. And then a little bit trickier to find, the bases are the spanning trees of G. In this case, like A, B, B, C, and C, D, we can see after maybe working through it a little bit, that this would be a maximal linearly independent set of columns. So that would be a basis of our matroid, and that's also a spanning tree of G. And we already kind of worked with the fact that if you have a circuit, then you're going to have some sort of linear dependence relation because it's in the kernel of this matrix. So there's another way that we can write the same matroid from a graph that ends up being really helpful for what we're going to do in the future. So I'm going to talk about that as well. So what we're going to do first is we choose a spanning tree. We're going to, in this case, choose A, B, B, C, and C, D. We're going to write the identity matrix in some order and then have it correspond to these three edges here. So we start with the identity matrix. Then we're going to choose a leaf of T to act as a root, which is really funny from a botany perspective. And we're going to orient all of the edges away from this point on the spanning tree. So we have this orientation. And then this next step is easier to say than to write down. But the idea is we're going to fill out the remaining columns. Each one's going to correspond to one of these other edges that's not in our spanning tree. And we're going to give it an orientation and give it numbers that make it so that it's a circuit. So in this case, AC is going to form a circuit with AB and BC. So one way to make that happen is we give it 1, 1, and then we orient it in the other direction so that we have AB plus BC minus AC equals 0. And similarly for AD, this time it's forming a circuit with all three of these. So we're going to put 1s in every position and again, orient it against the direction of the circuit. Or you could put -1s and orient it in the direction. Either way is fine. So this is always going to work for when you're given a graph. And this just gives another representation of our matroid. But something cool about this one is you notice in our last case, there were 4 rows. In this case, there are only 3 rows. And in fact, we say the rank of the matroid is the size of the bases, which are always all the same. In this case, the size of a spanning tree is 3, and the number of rows is also 3. So that's kind of a nice thing about this matroid. It also is cool that it starts with the identity. We're going to use that in the future. So we saw before that 2 edge configurations are equivalent if and only if they're equivalent modulo image of del transpose plus kernel of del. In fact, we can say the same thing about this matrix D. They're edge firing equivalent if and only if they're equivalent modulo image of D transpose plus kernel of D. So it's not any worse than the partial map we had before, but there's something else cool that we can say. So let's add 2 more rows to D to get fancy curly D. And we're going to call these last 2 rows D hat. We're going to make them red. And the way that we're going to add these rows is we're going to take this matrix. So we start with the identity over here. We're going to take the part after the identity, and we're going to take the negative transpose of this matrix, and then we're going to put it down over here. And then we're going to take the identity for the remaining 2 columns. So we end up kind of having 1s all along the diagonal, and we have an identity here, an identity here, and then we have a thing, and we have the negative transpose of that thing. So why am I doing this? Well, in fact, this D hat, which remember is what I'm calling the last 2 rows, the image of D hat transpose is equal to the kernel of D. So we can see that that's telling us that if we take a row of D hat, so for example, this would be -1, -1, 0, 1, 0, that is going to give us a circuit if we look above. So in this case, that's saying that negative this column of D minus this column of D plus this column of D is going to be a circuit, which we see -1 + 1, -1 + 1, 0, 0, 0. So this part is sort of acting the same way as our kernel of D. And why is that helpful? Well, that means that instead of writing image over Z of D transpose plus kernel of D, we can just write image of fancy D transpose. It's a little bit quicker, a little bit nicer to work with. So we can do this in more generality. So in general, we're going to say that we have, we start with the identity, and then we have some n by m integer matrix. And then we are going to say that the sandpile lattice of D is going to be the image of D transpose plus the kernel of D, and the sandpile group is going to be Z to the n plus m divided by this. We can think of this as putting chips on all of the columns, essentially. And then if we let D hat be this matrix where we have -m transpose followed by the identity, and fancy D be this square matrix that's D over D hat that looks like this, like we had before, then always, it doesn't have to be from a graph, we have this result that the image of D transpose plus the kernel of D is going to be the image of fancy D transpose. So what do we say about this? This means, I guess I didn't actually use this symbol up here, but the sandpile group of D we're going to write as S of D. So the size of the sandpile group of D is going to be the determinant of fancy D. It basically comes from this fact that we're dividing Z to the n plus m by this lattice, and then you use some linear algebra results to say that the size of the group is exactly the determinant of fancy D. And the reason why we care about the size of this group is because, remember, the size of the group in the graphical case was super interesting because it gave us the number of spanning trees. So we're hoping to get some similar interesting result here when we're looking at the size of this more general sandpile group. So let's say that we want to find this, this determinant. So we have a lemma that the determinant of D is going to be the determinant of, or sorry, determinant of fancy D is the determinant of normal D times normal D transpose. And the way that we can show this is we start with fancy D. We're going to multiply the bottom bunch of rows by M and subtract these from the top part. And that's going to give us this. And then M times M transpose plus the identity is exactly going to be D times D transpose. It's pretty easy to check if you work it out. And then we have this lower triangular matrix, which means the determinant is just the determinant of the D times D transpose multiplied by the determinant of the identity, which is always 1, which means it's going to be D times D transpose. So we have a little happy face. Oh, and let me just pause for a second. Okay, so now we want to find what D times D transpose is, the determinant of that matrix. So first I'm going to introduce some notation. So for S in the set of numbers from 1 to n plus m, we're going to have ds be D restricted to the columns of S. So we're taking a rectangular matrix and we're shrinking it a little bit. We're only taking some of the columns. Then we have this theorem that comes from the Cauchy-Binet formula, which says that the determinant of this matrix is going to be exactly, we take every set of n columns, where n is the number of rows, and we're going to take the determinant of that and square it. And this is going to make a lot more sense when I go to the next slide where I give an example. So first, before I give my example, we're going to combine everything that we've said so far to say that, or not everything, but some of the more recent stuff, to say that the sandpile group of D is going to be equal to this sum, because we already showed before that the sandpile group of D is equal to the determinant of fancy D, and the determinant of fancy D is equal to the determinant of D times D transpose, and then that is equal to this. So this theorem in another form and in slightly more generality was given by Duval, Clivens, and Martin in 2009. They were doing a lot more stuff with topology and more focused on that instead of talking about the matrices. And they also, I said there's a little bit more generality that I'll get to later. I'll talk about sort of what restrictions I impose and what they don't, but it ends up being essentially the same result. So let's give an example now. So we start with D. If it looks like this, that means that fancy D is going to have to look like this. And then if we want to find the size of the sandpile group of D, then that's going to be equal to the determinant of this fancy D, which you could solve, but we can also find it this way. So the determinant is going to be, we take every, since there's 2 rows here, we take every set of 2 columns of D, and we're going to find the determinant of that and square it. So in this case, we have the determinant of this squared plus the determinant of this squared plus the determinant of this squared. It's going to equal 14, and that is also going to be the determinant of fancy D. And that's the size of the sandpile group of D. And something else that we can note is that these DS's are going to be either, they're going to be a basis of D if they're linearly independent, or they're going to be linearly dependent, in which case their determinant is going to be 0 and they're not going to add anything to our sum. So we can change our sum a little bit and say that it's actually just equal to the sum over all the bases of, I write B of D, it's like the bases of the matroid that's defined by D would be kind of the full way to do it. You're going to take ds squared for each one. So now we've got the size of the sandpile group connected to a statement about the bases. which is kind of cool because back before we had in the normal Sandpile matrix tree theorem, we had a equivalence between the spanning trees and the size of the Sandpile group, and spanning trees are bases of graphical matroids. So it kind of makes sense that it'd be like this. So now we're going to talk about regular matroids. So if a matrix whose all of its square submatrices have determinant 0, 1, or -1 is totally unimodular, and a matroid represented by them is called regular. And from our previous theorem, if D is totally unimodular, then the size of the Sandpile group is just going to be the number of bases. And the reason for this is because we have a bunch of determinant squared terms, and the determinant of all of our bases is going to be 1 or -1. So we're just adding 1 for each basis. So in this case, we have this equivalence. So there's this very classic result from back in the 50s that graphical matroids are always regular. They always can be represented by a totally unimodular matrix. And in fact, both of the matrices that we gave earlier are totally unimodular representations of graphical matroids, I should say. You can show that. So what this means is that it gives us the Sandpile matrix tree theorem. It says that the size of the Sandpile group of a graph is going to be equal to just the number of bases of that graph or graphical matroid, and the bases correspond to spanning trees. So this is, I told you we were going to prove this theorem in a really roundabout way. Here's the proof. So now let's talk about cell complex chip firing, which is really what Duval, Klivans, and Martin were looking into. So simplicial complex is a higher dimensional analog of a graph. And I'm not going to go too much in depth about what the definition is. But a graph would be a one-dimensional simplicial complex. And we can construct a matroid on one of these simplicial complexes by taking the boundary map from n chains to n-1 chains. And that's going to give us a matrix just like we did for the boundary map from 1 chains to 0 chains. And then we turn that into a matroid. So we might ask, is this going to be regular? And there was this result proven by Cordoval, Las Fargas, and also by Lindstrom independently in 1979, which says that the complete two-dimensional simplicial complex on 6 vertices is not regular, which means not all simplicial matroids, it should say simplicial matroid, but yeah, not all simplicial matroids are regular, and in fact, you don't have to get too large to get a counterexample. This is pretty small in the grand scheme of things. So this means that we don't have this equivalence between the number of bases and the size of the Sandpile group when we're working with simplicial complexes. So since simplicial complexes are already badly behaved, then we may as well just work with any finite CW complex or cell complex. And this was sort of the focus of the work done by Duval, Klivans, and Martin. So what we want to do is we start with a cell complex. We want to convert it to the form identity and then M if we can. We can't necessarily, and then convert it. So is there a question? I saw something pop up.
There's a question in the chat.
Yes.
From Venkatesh. It says, is a characterization known for regular simplicial matroids?
That's a good question. I'm not actually sure, but I know that, I think that not a lot of research has gone into looking into simplicial matroids at all in general. So I don't think there's a whole lot of work on like which ones are regular or not, or even like really anything about simplicial matroids. They're certainly all representable because they're defined in a representable way, but people have put a lot more focus into graphical matroids. So yeah, so we want to convert the top boundary map to this form and then get the cellular matrix tree theorem. And we can't always do this. So it works as long as our cell complex contains at least one basis with determinant 1 or -1. When it doesn't, we can't really have this identity here, and then everything falls apart. I mean, I haven't really looked in yet exactly how much it falls apart. It might be fixable, but it's not like some trivial little thing. There's a lot of issues. It actually makes, sometimes you're gonna have it so that the nth homology is non-trivial, which we remember that the 0th homology being non-trivial said that the sandpile group didn't match the edge-labeled sandpile group. In general, if the nth homology is non-trivial, then the this sandpile group that I defined is not going to completely match the one that Duval, Clivens, and Martin defined. They call my version the cut flow group, and then they define it slightly differently. So stuff gets a little bit weird when you don't have a basis with determinant 1 or -1. So I just focused on the case where you do for now. And one nice thing is that if sigma is the complete simplicial complex in any dimension with any number of vertices, then you can always, there's always a basis of determinant 1 or -1. And I mention this partially because the kind of precursor to the cellular matrix tree theorem was by Gil Kalai in 1983. Before people were even talking about chip firing, he was interested in counting the number of spanning trees in some, like with the right definition of complete simplicial complexes, and came to the result that you need to have a weighted count based on the determinants given before. He basically came up with a version of the cellular matrix tree theorem for, but he was specifically focused on complete simplicial complexes. Okay. So now we get another question, which is, so we want to find a combinatorially interesting map from the sandpile group of D to the set of bases of D, such that the pre-image of any basis is going to be its determinant squared. So we know that such maps have to exist just by enumeration. We know that for each basis, there's ds squared many elements of the sandpile group. So the numbers are correct, but the challenge is to find a combinatorially interesting map that does this. So when D is from a graphical matroid, these bijections are called Sandpile Torsors, sort of. That's not completely true, but it would take like 20 minutes to say exactly the specifics of what a Sandpile Torsor is. The idea is that it's sort of like a collection of bijections, like a free transitive action, and there's questions about exactly what you're allowed to assume and how much you have to, and like what, basically it's a lot of work to figure out what combinatorially interesting means, but I think this is a good enough definition for now. Is there a question in the chat?
Dari has a question. Dari,
Okay.
you want to unmute yourself and ask, or?
Okay, so I'm wondering if this equality can also be interpreted as a dimension of a semi-simple algebra is the sum of the squares of its reducible representations.
So I will say I don't actually know much about this topic. Is that like are semi-simple algebra stuff that connect to matroids a lot, or
Not so far, I guess.
no? I'm not sure. I haven't. I don't really know too many details about that, but it might be. Any other questions? Before I'm close to the end, so I can. I'll take a bunch of questions later, hopefully. So anyway, we have these sandpile torsors, or something like that's at least a fine definition for now. And we have some on graphs. These are sandpile torsors specifically on graphs. The rotor routing process and the Bernardi process. There's been a lot of work on sandpile torsors. Actually, my first research project was related to them, so I've studied them a bit. And then when D is a regular matroid, then we again have a bijection because each of these is going to be 1. And this was given by Bachman, Baker, and Ewan. More recently, a bijection between the bases and the Sandpile group here. So then the general result for any D is going to be in my upcoming paper. I just figured it out like a few weeks ago, and I'm very excited. It's uses some ideas from the Bachman-Baker UN one, but I had to change a lot of stuff because things just don't always work in non-regular Matroid land. But I'll give you a little preview. This type of tile appears in my proof, and it would take a little while to explain what this means, but this gives like a periodic tiling of R2, and it's very pretty to look at. So thanks for listening. Hope you enjoyed it.
Let's give Alex a round of applause, and then we'll open it up for questions. Oh, I don't know.
So I have one more question. I'm not sure if this is anything near what you've been doing, because it feels like you're moving the subject away from original chip firing towards actual matrices. But in terms of chip firing, is there any confluence result, any kind of Sandpile monoid in higher levels?
So as far as confluence results, so I think a lot of the stuff you can turn back into chip firing from here. So I know my advisor, Carly Clivens, has done some stuff about confluence. You can set up chip firing on cell complexes to look more like traditional chip firing, where you end up putting chips if you go up one dimension, instead of doing some sort of putting chips on the facets, which is what I'm doing, you could have your chips be on the edges and then they move across facets. So you sort of think of like you have like a rubber band that you stretch across the facets, and it's always you'll be mapping from like instead of working with cyclic chip configurations, you'll be working with cyclic n-1 chains for some form, instead of working with general n chains is basically the idea. So that there has been some work on that, and there's some results as far as that's concerned. I see the chat lighting up. Is there?
Yeah, there's a couple of questions from the chat. So Tim has a question. Can you unmute yourself and ask? Or
yeah, so I was just wondering whether there's anything that generalizes to arbitrary non-representable matroids, or whether everything is intrinsically representable.
Yeah, that's a good question. So I don't think there's really anything for non-representable matroids. I was hoping that I could get to some non-representable stuff, but at least the way I'm defining it here, you really need some information that you get from a matrix. Yeah, one of my goals is to think more about what non-representable chip firing would be, but yeah, so far it's just been representable, as far as I know, at least. And then there was a question a while ago of Sam Northshield asking if the Duval-Clivens-Martin paper, Simplicial Matrix Tree Theorems, there's actually, I think, like 4 papers by them, and then also a book by Carly Clivens. They all have different information. I think the one that was closest to what I ended up adapting is called Cuts and Flows on Cell Complexes, I believe. That might be the most general, but it's also potentially a little bit trickier than some of the others since it has like a lot of homology in it. And a lot of my work was when I was trying to understand this, was converting these ideas in topology into more on like matrices and algebra, and like they work in a more general case than me, where they don't assume this spanning tree of trivial torsion where the determinant is 1 or -1. That's an equivalent way of saying it. So they get some different results with that. So yeah, I would say cuts and flows on cell complexes is the one that was closest to what I'm doing here, but from a different perspective. And I have a question about the Steiner tree, which I don't know what the Steiner tree is, so I can't say for that, unfortunately. Does anything general to sixth root of unity matroids that are net? Vic, can you explain what that question means?
Yeah, I meant to type generalize.
Okay.
There are some results about matroids not represented over the rationals, but over like rationals that join sixth roots of unity. And there are some interesting things happening there in the matroid literature. So I'm just wondering if I had like totally unimodular such matroids, is there anything interesting going on with chip firing there?
That sounds really cool. I don't know anything about it, so I can't really say, but yeah.
So from a quick view, it's a book by Clivens. She has like a little section 7.9 about this whole monoids fixture for higher dimensions, and I don't actually think she answers anything there. Is it, or do you know what's been done?
As far as what are monoids exactly?
So well, okay, let's say confluence. Basically, any question where it's not where unfiring is not being on the same footing as firing. Anything where you have some sort of directionality.
I kind of see what you're saying. Yeah, there's she has a paper pretty recent about that there is a paper about conflict. Yeah, I should have said this earlier, but she has something about flow firing that finds that on like a grid there isn't confluence, but then if you remove a point or you like remove some of the grid, then there becomes confluence. I don't remember exactly how the result works, but there are some interesting confluence results that she came up with.
Oh, I see. So it's not God-given anymore. I see.
It's what?
It's not God-given anymore.
Yeah. And as far as you're talking about the difference between firing and unfiring, one result is that on a graph you can fire all of the if you fire every vertex, it's the same as doing nothing. So that means you can fire all but one vertex, and that's the same as unfiring that last vertex.
Well,
but that doesn't work in higher dimensions. But I think also, I think the main thing is that most of the stuff that she's doing isn't having this fire whatever you want whenever you want rule that I use. So most of the confluence results, you need to have some rule about when you're allowed to fire. So yeah. I guess that's the main thing there.
Are there any other questions from the audience?
I mean, could I perhaps comment on this thing about regular simplicial matroids?
Yeah, sure.
Yes, right. So by CMOS decomposition theorem, there are like two main classes, right? Regular matroids are decomposed of graphic matroids, co-graphic matroids, and R10. And the graphic matroids you get basically from a simplicial complex embedded in 3 space. Because then you could draw the dual graph of the embedding, and this then represents the matroid. I mean, if you want to get co-graphic matroids, what you could do is you could take a double cone over a graph. So does this work? You take your favorite graph, and then take 2 vertices, and then have 1 edge for every vertex of the simplicial complex, and put a face of size 2 for every edge of the graph. And then, okay, it's not perhaps simplicial complex, or perhaps you have to subdivide a little bit the faces to make them all size 3 and have no parallel edges and so on. Okay, so you can get, you can get lots of graphic matroids by embeddable simplicial complexes, and you can get the co-graphic matroids. And I don't know whether you can get a simplicial complex where you get R10. I don't know this. And then there are lots of, then corresponding to these 2 sums and 3 sums operations on graphs, you have like similar operations on matroids. And probably what you have to do is kind of figure out kind of how this all fits together. And hopefully you could build all of them plus minus R10. I don't know.
Cool, thanks. Yeah, I know that my advisor has been interested in trying to find some information about how to like characterize all the simplicial matroids. So it's just a little bit tangential to what I've been doing so far, so I haven't looked into it too much.
Good. Other questions from the audience? Good. If there aren't any other questions, I don't see anything else in the chat. I'm going to stop the recording.